Hello. My presentation is on identifying the reason why there are temperature spikes in the BYUI greenhouse operations. What you can see in front of you is a figure of temperature versus the time of the day, where the temperature reaches a maximum in the middle of the day. The orange line and the gray line represents programmed tolerances within the software. The software in the greenhouse can be modified and changed to accommodate different climate situations and different extremes in the weather. This software also allows us to program or to visualize all the data that is being collected within the greenhouse. And as a result, it's been noticed that during the summer times, specifically within July and August, the greenhouse temperatures spike. And there is no understanding on the reasoning why that is. To better understand this problem, I developed a problem tree. It's kind of funny because it goes with the greenhouse theme, but it also gives us a pictorial representation of the issues within the greenhouse. When the issue was identified that these spikes were occurring during the hot summer months, several tests within the greenhouse sensors and controls were run. As a result of those tests, it was ruled out that the sensors were functioning properly and the controls were being appropriately managed. It then resulted in the greenhouse lead believing that it was a machine error or that the system was simply being overloaded. To understand whether it was a machine error or if the system was being overloaded, energy in versus energy out analysis was taken. Plants, the solar and sky radiation, and the fans were termed as energy in, and the energy out was termed as the convection going over the greenhouse radiating energy into the atmosphere, and the evaporator, which is the primary source of cooling within the greenhouse. The image that you see in this picture depicts 6 fans, an evaporator, and a sump. The sump is simply a large container that hooks up to the evaporator as a reservoir for water. When analyzing this part of the greenhouse, which is the interior, it was noticed that radiation was the primary source of heat, being 21,000 watts approximately. When considering the fans, it was found that the fans had a 60-watt rating each, which made them 360 watts in total. This is less than 1% when compared to the radiation heat that is being put into the greenhouse. Another consideration was the amount of plants that are in the greenhouse releasing heat through respiration. When looking at how many plants were in this greenhouse, there was approximately 120 plants. With these plants, it was considered that they would radiate and they would also use convection to transfer heat into the ambient air. We calculated the H values for the forced convection because of the mass of air being blown around the room, and it was termed that the plants approximately generated 780 watts of heat. That again is less than 2%. When calculating the emissivity of the greenhouse and how much heat is leaving the greenhouse, it was calculated that it was about 20 to 30 watts, which can also be considered negligible for this situation. When analyzing the outside of the greenhouse, it was determined that the convection over the greenhouse would be a significant factor in the energy lost from the greenhouse, being approximately 750 to 1,000 watts depending on the velocity of the air at the time. Although, initially when I did this, I assumed a thin-walled experiment with the polycarbonate panels on the top of the greenhouse. As I researched the properties of the greenhouse, I realized that the thermal conductivity of the polycarbonate was only 0.21, which then forced me to not be able to make my thin-walled assumption. I also found out that because of this, the thermal absorptivity and thermal emissivity were both also low. On the left you can see an evaporator. Water is pumped up into the separator then flowed through a cardboard mesh and then flows back into the sump. This allows for maximum evaporation to occur. The mass flow rates of the evaporation were calculated by taking the difference in the water levels of the sump over a period of time, which was calculated to be 0.0076 kilograms per second. The theoretical value was also calculated by applying a mass balance to the greenhouse, where the mass flow rate was calculated to be 0.008, which is only a 5% difference. How an evaporator works can be seen on the bottom right. Warm, hot, dry air is pushed through the mesh of the evaporator, which has water flowing down. Looking at the psychrometric chart above that, we can see that from point 1 to 2, the water is being heated up and evaporates, or is superheated and evaporates off the evaporator, thus cooling the hot air and then vaporizing the water, causing more humidity, which benefits the plants and cools the greenhouse. As the humidity increases from the evaporation of the water within the mesh of the evaporator, the efficiency of the evaporator drops due to the increase of the moisture of the air. Remember, an evaporator works best with hot, dry air to vaporize the liquid flowing through the evaporator. So looking at this diagram, we can see from tabulated data shown in this figure that the efficiency decreases as the ratio of water to dry air increases. In order to test this hypothesis that the evaporator was losing its effectiveness as the relative humidity within the ambient air of the greenhouse was increasing, the windows on the back of the greenhouse and the windows above the greenhouse were opened to atmospheric conditions. As that occurred, the relative humidity in the greenhouse dropped and the efficiency of the evaporator increased, resulting in the temperatures in the greenhouse to drop as well.